I started, it's rolling, huh? I started at Thiokol in 1974 after they had been awarded the space shuttle contract. I'd been teaching in mechanical engineering here at Utah State. But I decided instead of getting a PhD, I'd like to go out and see what industry was doing. And we could stay right here in the house and I could drive the hour drive out to Thiokol. So let me make sure you understand what the space shuttle program is. I was working in the tool engineering department, which makes all the tooling and stuff to make. I didn't design the rockets or anything else. I was working on lifting beams and for instance, this is me right there, and this is what's called the breakover fixture. So the space shuttle segments are cast vertically, and then they're taken out of a pit with a crane and put in this breakover fixture. And this is part of the transporter deck. This is a weight slug. We had to weight test everything to prove that it was okay to handle the space shuttle stuff. So space shuttle is made of 4 segments. They're about 12 foot in diameter and 30 feet long, weigh about 300,000 pounds each. And the wall thickness of the steel is only like 1/2 inch. But if you look at the aspect ratio of 12 foot in diameter and 1/2 inch walls, it's kind of like a pop can in a way. So anyway, so the space shuttle has a forward, 2 centers, and an aft. And here's a 6-foot man. A 6-foot man can walk through the throat of the nozzle. And when this is, it ignites from the forward end with another separate little rocket motor, the plume of which goes down the full length of the thing and starts the propellant burning from the inside out radially. So it doesn't burn from one end to the other. Picture of it. When I first designed the breakover fixture, I was naive in thinking that somehow or other we could get the lifting beam hooked up to the ears on the, this has ears, but the space shuttle booster segments have 180 pins. Yeah, it's every 2 degrees there's a 1 inch diameter pin in these joints that holds it together. And I was thinking that, you know, we could get that hooked up, but they very quickly decided, and by the time this was done, I was in a different group, but so they added ladders and stuff to be able to get up and work with the beam, getting it attached. As part of the manufacturing operation, after they're cast, they're taken to an x-ray machine and x-rayed to see if there's any deformities in the propellant. These are air bearings, and these are air-driven roller wheels. When we first put the space shuttle segments in one of these, it wouldn't rotate because it's so flexible it flexes like a loaf of bread. And we had to put another row of air bearings down both sides to give it enough, to keep it round enough to rotate. Because of the center of gravity changes for these different segments, we had different holes along these beams for these cross beams, and the links coming down to the segments there had to be, you know, correct so that the thing would all lift correctly. This particular lift was to put it on a transporter to take it. Ashworth was a separate hauling company from Salt Lake City that would take the segments from our finished operation, final assembly they called it, to the railhead in Corinne. Anyway, I designed this adapter to go from our deck to their hauler so that they could actually do so that they could come and pick up instead of having to have a separate move where the segment is transferred from our transporter to theirs, we ended up making this adapter so that they could also pick up. So what happens is these big noses go into the end of the deck, and then they raise it, so it's like a great big crowbar action. You know, there's millions of pounds of force, stress here in these. So there's your two cranes on each side with the beam, and they're lifting the segment off, and then this will be pulled. This rail car will be moved under it, and the thing would be set back down. There's another view. Before there were, if you drive west of Corinne, Utah right now, you'll see a big building. And all of this is inside that building. But before the building was built, we had this crane. And so the rail tracks are in the center, the roadway for the transporters on one side, and there's a space on the other side to set this cover down. So the transporter comes in, you move the crane over, lift the segment up, and then they move it over and set it down on the rail car. And then they go to the other side, pick up these little legs drop down from that same beam, and they hook up to the cover of the rail car, and they move it over and put it down over the cover. And that's the way it's shipped to Florida. You can't really see it, but instead of two wheels, well, two on each side, there's a lot more rail wheels under to carry the load. I worked all over the plant. This is a post-fired segment. That's the aft segment that's come back from Florida, and you can see all the soot and stuff from the blast off. This was a straddle crane that they would use inside that building in Clearfield to unload it from the rail car, put it on, like for instance this, and that's an empty transporter that I wrote the spec for, and Talbert Trailers in Indiana is the one that built the trailer, and I wrote the specs for that and went backstation. This is a picture of how the rocket appears just before launch. It's on a big platform. These are bolted down in the VAB, and it's all assembled, and then it rolls out to the launch area. That's a picture of an assembled rocket at Thiokol's test area, north of the Great Salt Lake, basically. Here's your 4 segments ready to ship. That Pathfinder, if something hits that, you know it's a problem. The first segment they set into on the MLP, the Mobile Launch Platform, is the aft segment. It has big hold-down posts, but they're not exactly equal. They're not in a square pattern, they're in a rectangular pattern. And that caused the upper end of that aft segment to go elliptical this way. And then when they were bringing the other segment in, it was elliptical this way because, and that's one of the things we had to correct after the disaster, is instead of a 2-legged lift, we made the crane so it could do a 4-point lift and make it more and rounder. But this represents the old style of clevis joint. One of my main tools that I helped to design was this field joint assembly fixture to help like a shoehorn. Even though the segments weren't perfectly round, it would, with these guide blocks and stuff on it, it would guide the segment in and it would round them up and put them together without. Before they were trying all kinds of things, trying to squeeze and get them to go together.
Mm-hmm.
What I don't have a good picture, I'll bet if you give me a minute I could, I'll tell you why it failed is when you've got this big cylinder and you've got 900 psi air pressure, so it balloon, you know, it starts straight and then you get pressure. The ends are more massive,
Mm-hmm.
so they don't go out, they don't expand as much.
Mm-hmm.
So it's like a balloon and these things rotate.
Yeah.
Well, as it rotates, these two O-rings, those are the O-rings that would be in those grooves, have to track the, this is called the clevis joint, and the tang that goes down in there has the smooth surface that these O-rings would press against. But they launched in really cold weather, and so the O-rings weren't as pliable and flexible. So when after it fired and starts expanding and so forth, these O-rings couldn't track. So hot gas came through. One of the fixes, and that's what I need a picture for you, is the tang. The tang is a blade that comes down, and as part of the redesign, they put another leg. So they had to make new. They made what they called a capture feature. So instead of the tang coming down into the clevis like this, they made a capture feature so that when the things started moving, they were locked better together. Okay, but also in the vertical, they had all they had was some putty that was between the two. So as they put the aft segment, and then they would put this big ring of putty, and then they'd put the next segment down with those tang and clevis and put all the pins in and so forth. Well, that putty wasn't really very good to keep the pressure. So what they did, besides redesigning the clevis joint or the tang so it had the capture feature, they made a J seal. So when the pressure comes, it pushes harder to seal it better. So it can't punch through it. You know, there's hot gas there, but it and the rubber that they made it out of, you know, resists that flame quite a bit long enough. So because of the capture feature and the J seal that they put, they were able to launch with more confidence. Okay. So well, basically the cold weather launch, the joint, the O-rings couldn't track, and hot gas got through that putty and blew a hole through burned a hole, and it must have been directed, the hot gas must have been directed to the big fuel tank in the center, and that exploded.
Yeah.
Okay.